Great. And then I will start to share my screen. Mhm. Okay, great. Mhm. Okay. I received some emails from some students, and they said like, "Oh, JJ, I don't have a deep experience and a deep read on soils, so I decide to just to do a step back and before I start to show you about soil taxonomy, maybe spend at least some minutes of our class today to show about soil formation, to talk about soil formation, okay, especially about soil formation factors. So my plan today is to present you all the soil formation factors. And of course, I'm quite sure that for those that have a deep experience on soil science, they really know and they read and heard a lot about the soil formation factors. But anyway, I try to bring some results from articles and books and chapters that innovate and bring new information about how soil formation factors affect soil. And then I think that then we will be sure that everyone can follow the soil taxonomy classification. Okay. So just to start, who defined what we know about soil today? It was a concept defined by a Russian researcher that's called Vasily Dokuchayev. This old guy, this man, this sir, he studied soils in different parts of Russia, and because of this he could understand that soils, they are different, of course, but much more important than this, they are straight related to some elements in the landscape. Because before some of the ideas that the Kushayev bring to the society, people just understand that soils were formed by weathering of rocks, and just that. Like if you have a basalt, a soil can be formed by weathering of basalt. And if you have a basalt, you have the same soil. You don't have any variation of properties or characteristics of the soil. For example, the clay content, the thickness, the CEC, the capacity of absorbing cations or any other thing could be related to other property than just the rock, the weathering of a rock. So people just understand that soils are formed by weathering of rocks and just that, period. Okay. And the Kushayev understand, he expand this conception. He understand that no, soils are formed by other factors, by other characteristics, other elements in the landscape that also affect the properties of soils. Okay, so we can see that, for example, soils in highlands and lowlands, they will be different, even if they are formed by the weathering of the same rock. Or we also can have soils in flooded areas and non-flooded areas, and they also have different properties, even if they are formed by the weathering of the same rock. So we expand the idea, the concept, the definition, the concept of what are soils and how are soils formed. Because now we need to understand that soils, they are influenced by more agents, more factors than just the lithology, just the rocks. Okay? And then the Kushayev really creates what we call as soil science today, because now we have a lot of people paying attention to soil and trying to understand it as specific, a particular body in the landscape that could be formed by the influence of several factors. Okay. Dokuchaev, he published his results and his finds in Russian, and of course, we don't have a lot of people in the world that could speak Russian abroad, Russia. So his ideas were not very well widespread around the world, but a guy, sir, his name is Hans Jenny. He read that paper about the soils and how soils are formed, and then he said, okay, this guy, he has a point. He's really clear about his idea, and I agree with him. And Hans Jenny has a deep expertise on soil fertility, on crops, and he start to understand which soil properties could be defined by some elements in the landscape, and then he defined an equation that we call the equation that identify the soil formation factors. So he defined that soil, it's equal or depends on the function of the climate conditions, the parent material, the organisms, the relief, and all of these soil formation factors, they interact between them, among them, through time. And he also adds that some specific soil formation factors also could be named or could be added according to the evolution of soil science, okay? And he was a researcher in the US, and because of this, he was very well accepted because he could write in English, and then a lot of people could read what he wrote. And then we have a strong definition about what is the soil, and then let's say the creation of the soil science as we know that. But as I said, today we know that actually the basic idea, the initial conceptualization was done by Dokuchaev, a Russian researcher that was really important to us. Well, so let's think in this soil formation factors, okay? Let's think in how they could influence the soil properties, the soil characteristics, the soil formation, okay? So when we talk about climate conditions, we usually think about air temperature and precipitation. So yes, we can start with them. We need to consider that the mean annual air temperature is quite important to soil formation because it could say a lot about the chemical and physical weathering, okay? If I have very high temperature, very high air temperature means that I could induce some specific process that depends on temperature. And at the opposite, if I register very low temperature, I also could avoid some specific process, but I could induce other process. For example, the oxidation of iron, it's favorite, it's induced very fastly in very low temperature. And the calcium carbonate dissolution, it's also induced in very low temperature. So some chemical reactions, just because they are chemical reactions and they depend on temperature, they can be favored or not according to the air temperature. And we are not talking about how this temperature also affect other soil formation factors, because we know that at very low temperature, the biological activity can be very low, and because of this, we cannot produce a lot of acidity, and this acidity also reduce chemical weathering. And opposite, if I register very high temperature and I register high humidity, then both conditions could favor an intense, high activity of organisms that could produce a lot of acid, and this acid could induce chemical weathering, could favor chemical, induce intense chemical weathering. Okay, so this climate conditions, these climate factors, these climate variables, they are quite important to consider chemical and physical weathering. If we have some variations of air temperature, they could be annual or even daily variations. They also could affect a lot the chemical and physical weathering, but especially the physical weathering. So think about a desert or a very high area in a highland above 4,000 meters above the sea. The daily variation could be high, very, very high. So we can register temperatures around 40 Celsius degree, 45 Celsius degree, or even higher than this a day. And at night, we could register negative temperatures. This huge variation could um, shrinking and swelling of crystals, shrinking and swelling of minerals, especially those minerals that contains iron could suffer a lot of shrinking and swelling. They can expand and contract according to the absorption of temperature. And if this change of volume is quite high, now you can start to break some rocks, to break and crack, create some cracks that could induce some physical weathering. And physical weathering, it's quite important to soil formation, because then we are reducing the size of something, and this could favor chemical weathering, because now the materials are thinner and the chemical reactions could occur faster. But also, when you broke something in a thinner, in a smaller size, these particles also could migrate. So now we can induce migration from, for example, from upper areas to lowlands. And then I can concentrate a thick layer of sand or even silt. Okay, some uh, it's not physical behavior, but some physical process also could create clays, especially in glacial areas. Okay, the glaciers, they can produce clay, but according what we know that basically clays are formed only by chemical weathering, with exceptions. For example, glaciers. The glaciers, they can produce clay only by physical weathering. But let's say in the majority of cases, the clays are formed by chemical weathering, okay? And sand, silt, and of course, gravels, and even larger than gravels, we have the physical weathering creating these particles by cracks and breaking and smashing this material in thinner sizes, okay? The temperature is quite important, because induce this expansion and contraction of some of the minerals. And we need to consider that the majority of rocks, they are not composed by only one mineral. They are composed actually by several minerals. And when we have minerals with different compositions and different colors, they can absorb more or less energy, solar energy, and because of there, they can expand or contract more or less than the others. And this could start to break the rocks and produce thinner materials that could be removed, eroded, transported, and also could start to suffer some chemical weathering. Okay, the chemical weathering really starts at the silt fraction, but we also can see some sand particles affected by chemical weathering. It's less common, but also we can see in some specific horizons and layers. For example, the sea layer, the sea horizon, the saprolith, when we see some chemical weathering inside, you can see some sand grains that start to suffer some chemical weathering. But as I said, it's much more common in the silt particles because they are quite thinner than the sand particles. Not only the air temperature it's important, but also the precipitation, and as well as the air temperature, not only the average, the annual precipitation, but also the seasonality, the variation of the precipitation is quite important. So let's say that we are talking about a area that has a monsonic climate condition. The precipitation it's around 3,000 millimeters per year. It's a lot, yes, because of this high amount of water. We have an intense chemical weathering, and again, of course, if I register high temperature and high precipitation, both will affect also the activity of organisms, and the organisms also could induce a deeper and more intense chemical weathering. But the precipitation is quite important by itself, because when you have a high precipitation, you are leaching the materials, you are leaching the soil. So you start to dissolve, for example, a crystal of a feldspar, and all the elements that are released by the weathering of feldspar, for example, potassium, aluminium, silica, some of them could be leached, and the leaching of these elements could induce more weathering, more chemical weathering of these feldspars, because I have more water that it's leaching the soil, and this kind of washing, it's reducing the concentration of potassium and silicon in the system, in the soil, and because of this decrease of concentration, you are inducing more chemical weathering. So it's quite interesting, because the precipitation, the water induced chemical weathering, and the chemical weathering could also be more induced by a second wave of chemical weathering after, because of the leaching, of the washing of the soil, because of the water penetration from through the soil. Okay. Yep. Yeah. Someone said something? No? Okay, okay. So we have this effect of the precipitation that induce the chemical weathering and reinforce the chemical weathering because of the leaching of soil, okay? And of course, the precipitation variation through time, through years, and through some seasons also could affect a lot the chemical weathering, because it's quite common, for example, in dry lands, that the precipitation is concentrated in just some months, even in some days in some specific areas, okay? I know that I visit some areas in the past that the majority of precipitation occurs in just 8 or 10 days. So it's a lot. So it's a really strong variation of precipitation, because you can register a lot of days, like some months, 6, 9 months without any rain, and in just some hours, maybe 8 or 6 hours, a rain of 100 millimeters. So it's a lot. So this very high variation of precipitation could induce some strong erosions process. So this torrential events, when you have a lot of water that's falling in just some hours, the soil cannot absorb all of that water. So some water could penetrate through the soil, but the majority of water will just flow from the surface. So you induce a lot of runoff, and this runoff could induce erosion, an intense erosion, especially of fine particles. So this specific precipitation variation, these torrential events, could remove clay from the surface and induce the formation of a sandy horizon or a sandy surface horizon, because an intense removal of clay only on the surface because of this torrential events and an intense runoff. I will explain this with more details in some cases. We have some of these examples when I start to talk about some specific diagnostic horizons, okay? But it's quite interesting to see then. And we have the opposite. We have some areas around the world that the precipitation is quite the same. So we have 10 months of the average precipitation is basically the same, and just 1 or 2 months without fitting that mean precipitation. So in this case, we don't have a strong induction of erosion or a strong induction of chemical weathering in some specific months. We have that precipitation very well distributed according the year, according the months, and then the chemical weathering could affect and act during all the year. The evapotranspiration, it's also quite important. I feel that a lot of people don't think about it, but especially when we talk about dry lands, it's quite important, because in dry lands, the evapotranspiration could could reduce the amount of water that's available for plants, but also for chemical weathering. And because of this, you induce less organic and biological activity. Because of this, you reduce the chemical weathering. But much more important than this is that the evapotranspiration reduce the water content, reduce the chemical weathering, and could induce salt precipitation, carbonate precipitation, and increase the pH of the soil in some specific areas. This is quite important, not only because, of course, a soil with a lot of salt could be quite hard to land, to use, to manage, but we also have some specific process that acts in the soils. If we have a soil with a lot of salt, we have a very high electric activity. We also have some plants that cannot grow in this area because of this, and this very high pH induce intense chemical weathering of silicates, and this can dissolve, can destroy some silicates, induce the migration of silica, and this silica can precipitate in deeper horizons, forming hard pans or fragile pans. So this is quite important because you create a layer that roots cannot penetrate, that water cannot penetrate. And this is really, really hard to break. This is quite important to land management and also to consider to understand the landscape evolution. Okay, so it's quite important to consider how much water we can lose because of the very high air temperature. And I'm not talking about soil temperature here, just because we don't have a lot of data, okay? Because the soil temperature, it's even more important than air temperature. And believe me, in a lot of places, in a lot of sites, we don't have a strong correlation between air and soil temperature, air and soil humidity. So it's not very well established. If I have a very high air temperature, the soil temperature will be also high. And actually, in some areas, it's basically the opposite. It's quite interesting, especially in dry lands. When the air temperature is quite high, the soil temperature keeps low, keeps very, very low. Okay, so it's quite interesting to consider that, because also the soil temperature could avoid the germination of some seeds. So if I have temperatures above 30 Celsius degree, I start to kill every seeds that we have in the soil, because basically they cannot start to grow. Okay, because the temperature is much higher than they can support. But unhappily, we don't have a lot of information about soil temperature in the world, exceptionally for some countries. We don't have a deep, sorry, we don't have a deep, sorry guys, I'm not in the best way today. Only some countries have a deep web of sensors that monitor soil temperature. Okay, and because of this, we don't have a lot of data. At least in Brazil, I know just some areas that we really monitor soil temperature. And well, here are some pictures from Antarctica. You can see the effect of physical weathering in these cases because of this shrinking and swelling, this expansion and contraction of minerals that start to break the rocks in slices. But we also register in these cases the effect of salt crystallization and also water crystallization. So it's quite common in some areas that register positive temperatures in the summer, that some of this water could be in the liquid phase. So for example, the snow starts to melt and this water can penetrate through some cracks of the soil. When the winter comes, this water frozen and the ice expand the volume of that crack, and because of this you start to crack, to expand the crack and to break the rocks. The salts, they can do the same effect. Okay, when you have a lot of salt dissolved in liquid water, when this liquid water penetrates from the cracks and this water evaporates, then the salt starts to crystallize. The salt also expands the cracks and start to break the rocks. So it's quite common. It's beautiful because you can see a very large piece of rock that shows you that's quite strong, it's quite hard to be broken, but only some materials, only some millimeters of water or even salt in the cracks can break them. Yeni, during his research in the past, he found a strong correlation between temperature and clay content. So, of course, we need to consider that not only temperature but also humidity are important. But when he did this in the past, he could find that taking samples in different parts in the world, that we have higher temperatures and higher clay content. So if you increase the temperature, you increase chemical weathering, and because of this, you increase the content of clay. If you decrease the temperature, you decrease chemical weathering and you decrease the clay content. Again, I know we need to consider much more than only the temperature, but also the humidity of the soil, humidity of the area of the site, but as a general way to understand chemical weathering and temperature, it's a very good start. Okay, some researchers also in the past identify some weathering states according to the precipitation. They showed that in some areas, very low precipitation, so precipitations below 500 millimeters per year, induce what we call bestialitization. That it's basically the formation of 2 to 1 minerals. So because of incipient weathering, you induce the formation of 2 to 1 minerals, very high activity clays, and these clays, they are stable because of the chemical weathering, because the chemical weathering is quite incipient. If you have higher precipitation, for example, between 500 and 1,500 millimeters per year, then you go one step forward and you start the monocytization. Now you start to create 1 to 1 minerals. And why? Because of the intense chemical weathering. So the chemical weathering is intense It's more intense in these conditions, and because of this, we start to leach, you start to reduce the content of silicon in the system, in the soil, and then now you only can create one-to-one minerals. Okay, just one example of one-to-one minerals, kaolinite, halloysite, both are one-to-one minerals. Both are formed in deep wafering, in deep chemical wafering conditions. And some examples of two-to-one minerals, elite, smectite, montmorillonite, all of these minerals, they are two-to-one minerals. They have two layers of silicon and one layer of aluminum in their decomposition. Okay, and we also have more intense chemical wafering, the most intense chemical wafering, when the precipitation is higher than 1,500 millimeters per year, that starts to create 0 to 1. This term 0 to 1 is not really common. It's more common to say oxides. So we start to create oxides of iron, oxides of aluminum, basically, and more important, oxides of aluminum. These aluminum oxides, for example, the gibbsite, the boehmite, they express the most intense chemical wafering and the stage that we call alitization, when the leaching of silica is really, really, really high. Okay, this scheme, it's quite interesting, and this stage are quite interesting, but much more important than this is to consider that in some areas that the precipitation is much higher than 1,500 millimeters per year, we still have some kaolinite, and maybe we don't have gibbsite. And in some areas that the precipitation it's below 500, you also can see some soils without 2 to 1 minerals. So this stage, they make sense, they are quite clear, but we need to consider that we have a lot of exceptions. Why we have a lot of exceptions, JJ? Because the soil is not only formed by the climate conditions. Other soil formation factors could affect how the precipitation will affect the soil, and how deep is the chemical wafering. Okay, but let's talk about this in the next slide. Here is just to show you some of the solution of these materials when we have some rocks that are affected by water, by chemical wafering. So in this specific cases, we can start to broke some materials. For example, you can see these cracks, and we can see this large white grains, they are feldspars, and this fine orange material, it's clay formed by wafering of these feldspars. Okay, so we can see a lot of these materials when we check them on microscope. We can see this both images from the same area, showing, especially when we check this specific zone, this very light color, this very strong light color shows us the formation of clay. So we are seeing clay formed in situ. I'll say, okay. In this case, we call a dissolution that's incongruent of the saprolite. So we said that the dissolution, it's creating something new. And we also have some cases that now start to create some voids. So some of these voids are formed by the congruent dissolution of the material. Because of the dissolution of the feldspars, you just start to create some voids. And these voids now are places that can host oxygen and induce even more chemical wafering, or they can host water and also induce even more chemical wafering. Okay, you can see here also some holes formed in the rocks because of this chemical wafering. And something that's quite interesting to check is that if we see a global soil map, we can see that some specific soils, they have, like, let's say, a zonal distribution, a distribution that's related to latitudes. So we can see this red spots in South America and also in Africa and some areas here in the Asia, showing us that these specific soils, the oxysols, they are straight related to equatorial or tropical conditions because they are more related to intense, deep chemical weathering and leaching. We will talk about these soils later. Don't worry about that. If you never heard about oxysols, you just need to see that we have some soils with latitude distribution. For example, this ones, this light green or blue, I don't know which color do you prefer to call it. These zones, of course, they are more related to the Arctic. We can see they are called jelly soils. The jelly soils are related to soils with permafrost, with cryoturbation features, with ice. So, of course, I only can see then where I have a stronger influence of glaciers. So, of course, I can see them very easily in the Arctic, also in Antarctica, but I also can see them in very high highlands. But of course, because of this scale, I cannot see them, for example, here in the Andes or in Himalaya or even in Kilimanjaro. I cannot see them just because of this scale. And when we compare two soils from different areas, they are really different. They are, here we have some examples of one oxysol and one jadisol. Both are formed from the same rock, but they are quite different. And this difference is basically induced by differences of chemical weathering and also because of the climate conditions that affect the vegetation cover and affect other properties. So in deep soils, we have a very strong influence of chemical weathering because very high temperature, very high precipitation. The water, it's kept in the liquid phase for the majority of the year. We have an intense chemical weathering. Here, we don't have intense chemical weathering because the majority of time the water is kept in the solid phase. You can see the permafrost here. So this solid phase cannot induce a deep or strong chemical weathering. A physical one, yes, I can induce a strong physical weathering, but not chemical weathering. Because of this, the soil will be not very thick, okay, or weathered as in the first case on the left, okay. This figure, it's quite common. It's quite common. Basically, you can see everywhere, and it shows you about how deep the soils can be formed according to the climate conditions. So in wet, tropical, and equatorial conditions, because of the high temperatures, high humidity, we have a high primary productivity, a high organic biological activity, and because of this we have very thick soils, okay. So the weathering of the soils, it's quite intense. You can think as this gray color as the rock, and here in the blue a little chemical weathering. So this phase of little chemical weathering, it's quite deep, and a zone with 2-to-1 minerals that it's also quite deep, or at least deeper than the others. Here, a zone that induced formation of taulinite, a zone with aluminum oxide and iron oxides. And we can see that these zones, they just disappear when we go to zones with low latitude and arid and semi-arid regions. Because of the high temperature but very low precipitation in these areas, the chemical weathering will be not intense. And then because of this, I only can see formation of 2-to-1 minerals, and even some little chemical weathering. In some areas, I can see rocks on the surface, so rock outcrops. If I go to temperate regions, and then I have a higher content of water, higher temperatures than low latitude or arid and semi-arid regions. So the chemical weathering increases again, but of course it's not so intense like here as the equatorial regions. And at the polar regions, it's the worst case, because I just have water in the solid phase, or at least in the majority of the year, and I have a very, very low temperature. And of course, because of this, the chemical weathering will be much incipient, much low. Okay. So just to consider, how can we compare the chemical weathering, only considering the chemical weathering and only considering the effects of the temperature and precipitation. But of course, again, we need to consider this effects on how deep could and how intense could be the production of organic material and the decomposition of this organic material and producing of productivity of acidity. This graph also, this PCA, it's a statistical analysis that shows us a very interesting idea, okay? For this specific plot, we took more than 800 samples in different areas, and we showed that the chemical composition of the soils are quite different from according to the areas. So for example, soils with a higher pH, they also have a higher content of bases, calcium, magnesium, sodium, potassium, and they are also enriched in elements that are divalent. For example, barium, strontium, and manganese. On the other case, when I have more weathered soils, they are rich in aluminium, in clay, so they are clay-rich soils with higher content of aluminium. They have higher content of soil organic matter, and it's quite easy to understand that, because if I have a higher content of clay, means that the soil is more weathered and can support trees that produce more organic matter than just, for example, grass. Okay, and this more weathered soils with more content of soil organic matter also are enriched in some elements. So for example, iron and copper that are trivalent. So here are those elements that can be easily leached. We only see them in very incipient soils, in areas like dry lands. And here we can see soils formed in intense chemical conditions, intense chemical weathering conditions, I'm sorry, and more related to forests, especially rainforests, okay? So, okay, we know that climate conditions affect the soils. Okay, great, quite easy. But let's think about other soil formation factors now. We need to consider that organisms, they also affect the soils, okay? Maybe the main way that they affect soils are by the addition of organic carbon, okay? We can see that tropical and temperate soils, they have an average between 1 and 5% of organic carbon. That's a lot. And in some deserts, we don't have carbon. Could be dry or not dry, could be hot or cold deserts, but both, they have a very low organic carbon content. Some of them are virtually absent. So maybe in some soils we cannot find organic carbon, okay? But okay, JJ, why organic carbon is important? Well, because of a lot of its properties, okay? Organic carbon component, it's the main component of organic matter, of soil organic matter. And soil organic matter has a very important property that's related to absorption. Organic carbon, organic matter has a very high absorption. It has a very high specific surface. So because of this, organic carbon can absorb a lot of elements. Some of them could be toxic, like arsenic, but also can absorb some nutrients like calcium, like magnesium. So the absorption of elements could be done by organic carbon. And because of the very high specific surface of organic matter, this organic matter can absorb a lot of these elements, very high content of arsenic or calcium could be absorbed by the organic carbon, okay? And also not only elements, but also water. Water can be absorbed by organic matter. Of course, not all types of organic matter are absorbing water, but those that, yes, can absorb, they absorb a lot of organic carbon. You can just think about the differences of volume of a grape and a dry grape. They are quite different, and the difference of volume is basically water. So especially in dry lands, especially in areas that the liquid water is not available in high amounts, the organic matter it's quite important because then they can absorb more water and reduce the drought stress of the plants. Okay, so organic matter it's a quite important issue to consider in soil management in dry lands. In areas that the water is not a huge problem, then the organic matter it's important because of the content of nutrients. For example, here in Brazil, a lot of farmers start to add more organic carbon in the soil in the last like 20 years because they realize that when they add organic matter, they also increase the organic carbon content, but much more important than this, they increase the content of nutrients. And then they need less fertilizers. And then they spend less money to produce the same amount or even higher amounts of crops. So yes, it's much more important. It's cheap, it's important to the environment, and also important to the farmers. So yes, they are quite important. And also, the organic matter, it's important to what we call formation of aggregates, the pedalization, the aggregation, the formation of aggregates. One of those keywords that we use to identify soils, remember? So to create some aggregates, you can think that, for example, some roots could start to grow and then they put some particle together, and some of these particles, when they are together, you can also induce the growing of some microbiological activity, but also some ephas, some termites, some ants, and some other organisms that could induce let's say a grouping of these particles, and these particles can start to act as just one, not only individual particles. The organic matter it's quite important because induces what we call flocculation, that put everyone together. Can be a physical way to put everything together because the roots start to grow and then they put the particles in contact with each other, but also because of some chemical reactions. Okay, the organic matter it has a negative charge, it has some negative charge at the surface, and especially the minerals, the majority of them, the majority of 1-to-1 and 2-to-1 minerals, they have positive charge at the surface. And we know by physics that if you have negative and positive charge, what they do, they flocculate. They are together. They are being closing to each other. So the presence of organic matter induce physical and chemical attraction of particles, putting them together and starting to create pads or aggregates. The second, the second phase is what we call cementation, because the partial decomposition of this organic matter induce the formation of some ethers and some layers of organic and mineral interaction between the material, creating more stable conditions. So you start to solidificate the pads, the aggregates, and this induces what we call pad formation, or formation of pads, formation of aggregates. So the organic matter is quite important because it induces biological activity and also induce physical and chemical reactions that put all the particles together. It's quite common to see that soils with a very low organic carbon content, that the pad formation is not intense, or it's not, let's say, stronger than soils with a higher content of organic matter. Okay. Other influence of the organisms in the soil formation, we can consider, for example, the forests. This is a photo that I took in the past in the Amazon rainforest. And it's quite interesting to see that the photo is quite dark, but the clock time was midday. So it should has a lot of light, but I cannot see. And why I can see this light? Because of the density of trees. So the organisms, they produce, in this specific case, like a cape, like a greenhouse that avoids a lot of sunlight at the surface. And they also produce, of course, a lot of litter, and these actions reduce the temperature variation, increase the temperature, and increase the humidity inside the area. And of course, this induce more chemical warping and leaching, of course, more chemical warping and leaching of minerals and also the organic particles. Both will be decomposed faster than in regular conditions. If we saw the opposite, if we saw an area without any kind of vegetation cover, this process will be much more slow. The process will be slower. The chemical warping will be slower. The thickness of the soil will be much more thinner because we have less chemical warping induced, or at least favored by organisms in these conditions. Okay. A very interesting study I read in the past shows that the organisms, the plants, also can change the chemical composition of soil. This is quite interesting because they took samples in the same area, but at different times. So they took a sample in a bare dune without vegetation cover, and then in the same area after 15 years when they planted some pines, and after 30 years, and then 50 years. And they show a variation of chemical composition in the soil. They show that the calcium, potassium, and phosphorus contents are enriched, increased in the surface horizons. You can see here a very common way to see that. It's very easy to see that we increase the content of potassium in this case at the surface, even in the first 1 meter. Okay, why we change this chemical composition, why we change the content of potassium in the first 1 meter? Because the plants start to grow in this area and induce the cycling of some elements, especially those elements that they need in higher concentrations as calcium, potassium, and phosphorus. And also they reduced the content of some elements that they don't need a lot, for example, sodium. So the sodium content at the surface decreased, and some of elements like calcium, potassium, and phosphorus increase that, showing that plants also could affect the chemical composition of soils. We saw, sorry, we also can see some studies that are quite interesting because they showed us some positive correlation between base saturation and richness of vegetation cover. These both studies, they are performed in Amazon rainforest, and they showed that the parts, the regions with the highest richness of vegetation in the Amazon rainforest are related to those soils with higher base saturation, higher content of nutrients. This is quite interesting because shows also that also even the type of species that will cover an area depends on the soil, but also we have a higher or a different kind of chemical offering, more intense or less intense, with more or less organic carbon according to the base saturation of the soil. Some studies also show it in areas that we have a very high precipitation, that we should register gibbsite and we should not register kaolinite, but we still see kaolinite in the soil and we cannot see gibbsite. So they start to look for the answer, why the silicium still there in the soil and why the silicium was not completed leached and the soil has only gibbsite. Well, they found that the answer is the plants. The plants, the organisms, but especially the plants can recycle silicium in the soil because they can absorb, precipitate as phytoliths, and then when they die, they introduce or they reintroduce, they add that silicium into the soil again. And this kind of biological cycling of silicium keeps the content of silicium higher enough to keep the kaolinite in the system, to keep the kaolinite in the soil. If we don't have the cycling of silicium, so all the silicium should be leached, and yes, you cannot find kaolinite in these cases. It's when, for example, we compare some very old and leached soils in the Brazilian savanna or in the savannas, and we compare it with the rainforests. The rainforests, they keep the kaolinite in the soil because they have a stronger cycling of silicium. In the savannas, we don't have kaolinite, or at least the kaolinite is not only, the soils are not only formed by kaolinite, but also by gibbsite, because now you are reducing or depleting the content of silicium, and then you are starting to form gibbsite. Okay? Of course, for the people that pays more attention to soil management, some plants can accumulate and even exclude some heavy metals. We have a list, a huge list for each heavy metal that, yes, you can plant. For example, I register very higher arsenic content in the soil. So to reduce the content of arsenic, you can just start to grow some specific species and then can reduce the content of arsenic in that soil. Not only the plants affect the soil, but also the animals. And one of the most important process that the animals do, it's called pedoturbation, the mixing of soil by animals, especially termites, some spiders, some earthworms, some ants also can do this. Okay, all these animals, they can mix the soil. They can bring particles from the deepest horizons to the surface. And when they do this, they are mixing materials with different states of weathering. And this is a kind of cycling of nutrients and silica too, okay? So you can see here very, very easily, if you never paid attention to termites or ants, just pay some minutes, okay, to see what they are doing, and you can see that they are just basically mixing some soils. This photo micrograph shows the um, the background of aggregate. So you can see inside of this very small aggregates. And what we can see, this gentle circular shape that shows you that this material was inside an organism and it was defecated by one organism. So the shape of this aggregates shows you that yes, they are not only physical and chemical interactions, but they also suffer some biological intervention, biological activity. Much more important than this is that inside the aggregates, inside the pads, we can see coal fragments showing that the organisms, they ingest that charcoal fragments and defecate it inside the pads. So yes, that material was formed by biological activity. Why? Because fire events cannot put coal fragments inside an aggregate. Doesn't make sense without biological activity. The coal fragments should be only outside of a pad, okay? Something that's also quite important is that the quartz grains, the sand grains inside into the pads, they are up to 5 times smaller than the quartz grains in a B horizon or even in the C horizon. So showing you that yes, that grains that are inside the pads, they were selected by someone. Someone on animal selected that quartz grains to insert in the B horizon, to insert in the pads. In the C horizon, we have much less biological activity, and then the grains are much higher because they are formed by only by chemical warfare. In the B horizon, they are being selected because the animals, they cannot pick up or they cannot carry all the grains. They need to select according to the size of the grains because some of them could be too heavy to them. Okay, so they select only the finer grains to be in the B horizon because it's lighter than the others. Okay, another study that was quite important shows the crystallinity and the chemical composition of kaolinites are different between B and C horizons. So in the C horizon, we have less biological activity, basically only chemical wafering. Because of this, the kaolinites has one specific chemical composition and crystallinity. When we check the B horizon with much more biological activity, this chemical composition is different. The crystallinity, it's also different, showing us that the biological activity also change a little bit the minerals, okay? And of course, we have a lot of studies. I just add 2, but we have a lot of studies that show the addition of carbon, nitrogen, phosphorus, and other elements by termites, by ants, by spiders, and by others, okay? The parent material, I think this is the soil formation factor that's easier to understand because this is one of the first soil formation factors that could be thought about soils. It's quite clear that when we saw a soil format, for example, a gneiss or granite, they are quite different from soils format, for example, colluvial or alluvial sediments. So yes, the parent material affects deeply the soil properties, deeply the soil characteristics, and because of this, they will be different. Here, for example, we have a piece of basalt and granite, and of course, both are quite different when we see using only our eyes, because the basalt doesn't have grains that can be identifiable by eye. But the granite has a phaneretic texture, so you can see the crystals. But when you put them in the microscope, they also are different. You can see a larger amount of light crystals that are more related to quartz, to feldspars. And when you see the basalt, they are more darker minerals because they have more pyroxene, olivine, and other minerals with iron and manganese that has this dark color. Okay, so even when we check on the microscope, the plant material will be different, will produce soils in a different way. They could suffer more or less chemical warfare, as we already said. And we have a lot of studies showing how the parent material controls the soil formation and soil distribution, okay? This soils, these studies, they show it, for example, when you reduce the content of silicon in the parent material, you induce an increase of organic carbon, an increase of pH, an increase of CEC. I forgot to translate this into English. It's CEC is the cationic exchange capacity. It also increases some of bases, the content of calcium, magnesium. It also increased the content of phosphorus and also increased the content of clay. So yes, when we change the chemical composition of the parent material, we change a lot the properties of the soil, especially the chemical and physical properties. We have some studies that showed some correlations between parent materials and some soil orders. So using the soil taxonomy, for example, we can see some ultra-acid soils, ultra-acid rocks, for example, showing or forming some sporosols or antisols, and some carbonates forming some aridisols or mollisols. So according to the parent material, we have some soil orders that are more or less correlated. And then you can ask, so JJ, why we just don't ignore the soil classification and use, as people did in the past, only the classification of the rocks? Well, because you can see that we have a lot of repetitions. For example, aridisols, 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 aridisols. They are really, really correlated to several different parent materials. So it's quite difficult to keep only the parent material. But much more important than this, these orders are just the most common orders related to these parent materials. Of course, I can find other soils formed by warping of basic rocks. Definitely I can find. And definitely I can find some of these orders that are not related to this specific parent material. So this is a very good way to start to understand, as the soils are strongly correlated to the parent material, but we need to remember all the time that the soils are not only formed by the parent material, they are affected by other soil formation factors and by process that could change then, and because of this could change the soil classification. And also, much more important than this, even inside, for example, spodosols formed from ultra-acidic rocks, they will be totally different between them. They are not the same. They don't have even the same morphology. So soil classification go deeper on the difference between soils, not only to call something as a spodosol because it has this kind of morphology, but I can go much more deeper on this, okay? This is just an example in Brazil. You can see this. This is one specific state in Brazil. And this is the geological map of this specific state. Each color shows you one specific lithology, and then I will show you this. So you can see here the gamma spectrometry of the soil. The gamma spectrometry is a kind of image sensor that takes the chemical composition of the first 10 centimeters of the soil. So you are seeing here the chemical composition. Each color shows you if you have more potassium, more thorium, or more uranium in this first 10 centimeters, okay? So when you have these blue colors, you have more thorium. When you have this pink and red colors, you have more potassium, and you have this green color, you have an average content of potassium and an average content of uranium, okay? So you can see very, very easily that these differences of colors are related to the differences of parent material. Just check it again. For example, in this specific zone, we have this yellow rock, and here, you can see it here. Okay, the shape is not 100% equal because each one has one specific scale and a minimal resolution, but you can see both. Oh, sorry. You also can see this area with this, I don't know which color is that, light brown, you can call it light brown. You can see it again here. So all the rocks that we have there, they are very well marked in the first 10 centimeters of the soil. Even in that section it has a very strong biological activity. Even then, I also can register differences of chemical composition according to the rock. Okay, so great. This is quite important to see that. And also the chemical composition of the soil tells you a lot about process and also about the parent material. So, for example, for people that studies the soil formation, they use a lot the content of zirconium and titanium as tracers of parent material. So just see this graph, this plot, okay? We have the depth and here the ratio between zirconium and titanium, okay? And you can see here the surface, and here you can see around 100 centimeters, okay, of depth. So the surface show you this ratio that's close to 0.8. So you have basically the same result here. So you have a slight decrease and a slight increase, achieve the same value that you have in the surface, and then a strong decrease. And after this strong decrease, you have some variations around an average result close to 0.3, for example. So what we can say about the parent material of this specific soil using the zirconium-titanium ratio. This huge variation here, close, let's say, to 40 or 35 centimeters of thickness. This specific huge variation shows us that this section of the soil below, I don't know, let's say 35 centimeters to 100 centimeters, this zone, all the layers and horizons formed in this section of the soil, they are formed from one specific parent material. For example, a sandstone. And all this area, it's formed by a second parent material, by another rock, or by another material. Why? Because the ratio between zirconium and titanium is quite different. Zirconium and titanium, they are used by tracers of parent material because they cannot be easily leached. Okay, so the chemical warfarin cannot alter the zirconium and titanium contents in the soil. So if you have a difference of zirconium and titanium contents in the soil, it's because you have a difference, a change of parent material, not a change of chemical composition related to parent material or related to chemical warfarin. So again, if I have a very different ratio between zirconium and titanium here and here, this means that I have differences of parent material. So this section of the soil was formed, for example, from the warfarin of a sandstone, and this section of the soil was formed from, for example, from the warfarin from basalt or gneiss, a different rock, definitely a different rock. Okay, so these differences of zirconium and titanium ratios and contents are tracers of parent material, so we can use them. This is quite interesting. We can use them to identify, to track the parent materials of the soil, and we can see. And guys, this is much more common than you can think. We have a lot of soils that are formed from different parent materials. A section or some sections were formed from a specific type of rock, and the other sections were formed from another rock. It's quite common, okay? We also can use some of these elements, for example, the iron and zirconium, to show some variations of process, some variations of, for example, fluiding conditions. If I show, let's say, the same variation here, but not related to zirconium and titanium ratio, but now between iron and zirconium, these huge variations are related to glaciation process. So I can see that in some parts, in some sections of the soil, we suffered glaciation, we suffered flooding, even without seeing the colors, the gray colors, even without seeing the models or the iron concentrations, okay? Just because this huge variation of iron and zirconium ratio, I can say that yes, in the past or in the present, this soil suffered a strong variation of anoxic and oxic conditions, okay? Also, some studies related even the type and the size of soil structure according to the parent material. So again, we can use the composition of soil to track the parent material, and we can use the soil structure to track the parent material. And this is also true even when I consider organic soils. Okay, do you remember that we talk about the O layer or the O horizon? Those horizons and layers that are rich or they are enriched in organic components. If we check the chemical composition of this organic matter, and if this organic matter change a lot, yes, we also can identify different behaviors and different parent materials, even in organic soils. So for example, let's check that here is the surface, and here is the 200 centimeters depth. We have here a very low variation, some little variations, and then a huge variation, but again, goes into this direction, and a little variation, and then start to vary again a lot, and then a lot. Okay, all of these huge variations indicate variations of parent material, but in this case, an organic parent material. So if this specific soil is enriched in organic matter, all these phases with this abrupt or high change of organic composition, yes, they indicate variations of parent material, okay? In this case, I use it, for example, the delta carbon 13 or the delta nitrogen 15 to identify variations of chemical composition of the organic matter, okay? So yes, we can use a lot of proxies to identify variations of parent material. Oh, sorry. Again, oh, we can use the chemical composition to identify variations of the parent material, okay? Oh, sorry. Ah, the relief, yes. The relief is also one of the soil formation factors, and a lot of people, they usually say that the relief has antagonism with the soil formation factors, okay? Because the relief induce the soil erosion, and because of this induce or limits or avoids soil formation. Yeah, I'm not this kind of person. Personally, I think that we don't have this. We don't have an antagonism between pedogenesis and morphogenesis, the soil formation and the relief formation. I think that both are together. They both walk together to the same direction all the time, okay? Because the relief affects soil and the soil affects relief, okay? So we have thicker soils in some areas, especially in flat areas, because flat relief induce or favor more wafting and leaching. But we only can see thick soils in flat reliefs if this flat condition it's also in a very high altitude, very distance from a high distance from the water table level. So then you induce leaching and wafting. If you are in a flat area, in a lowland, you cannot form very thick soils because at this lowland, it's at this very low altitude, you cannot induce a deep wafting, a deep leaching. So you're not forming deep soils, okay? Also, some studies show it as the altitude and wafting are inversely correlated. This study, it was performed to Australia, and they show it as we can see, of course, very high altitudes and very low wafting in some areas because you have intense or more intense wafting, chemical wafting in these areas because of the erosion. And in some areas, we have less wafting because the altitude is quite high, but also in lowlands, you can register more intense wafting because you have less erosion. Well, this is not 100% sure and true because we can see even in lowlands, some areas that the wafting it's quite low, and also we can find some very high areas with a very strong wafting, a very deep wafting. So don't think that this is true 100%, okay? I think that each area we need to consider what affected and what formed the soils in that region. Okay, we have also some elements that influence soil formation, okay? So the water table fluctuation, yes, it affects the formation of the soil. So if you have a soil that is more affected by water table, especially water table fluctuation, if the water table is closer to the surface, you have more glaciation, you have change from iron 3 to iron 2. But if this water table changes a lot, you have a lot of change also from iron 2 to iron 3. You have more or less organic carbon concentration. So yes, you have a strong variation of materials. Okay. Guys, I think that we have, I need to stop because I'm receiving a message from my home. So let's stop for 15 minutes. Is it okay? I need to stop just to check this. So let's return at 10:45. Okay, just a second. Thank you. Thank you.
Okay, okay, sir.
Mm. So, hello everyone. I'm sorry, as I said, I'm not feeling very well today, but wait, let's finish, and then I can return to home and rest a little bit. I think that I just need to rest to feel better. So again, as we were talking about the influence of water table fluctuation on the soil properties on the soil formation. When we have soils at lowlands or very close to water table, the higher amount of water, the higher amount of water in the voids and the reactions, the chemical reactions influence on especially iron and manganese will affect the soil morphology. We have gray colors, we have soils without iron oxides, without manganese oxides, and the absence of these minerals will affect the chemical composition of the soil, will affect the chemical reactions because these elements, they register positive charge at the surface, and without this iron and manganese oxides we have less positive charge in the surface and less flocculation, less cementation, less pads will be formed because of this. We have also in these areas the fact that by the water table more accumulation of organic matter because of this reducing conditions. We have less decomposition of organic matter, and then more accumulation of organic carbon in these specific zones. So we have chemical, physical, morphological properties that will be directly influenced by the water table. And also, if this water table fluctuates through time, this will affect even more the soil properties, because I have some months or some time when I have oxic and some months or some time with anoxic conditions. And this fluctuation between anoxic and oxic condition, we also change will also change or affect the physical, chemical, and morphological properties of the soil. Okay. We also have a strong influence of erosion. As I said, not only that strong erosion that erodes all the soil will affect, of course, the chemical and physical properties, because if I register a strong erosion, especially in steep slopes, it's more common that the rocks will be closer to the surface, and because of this the wafting acts on these rocks and also create some 2-to-1 minerals, higher content of bases as calcium, magnesium, and other elements. So if I have soils in steep slopes with strong erosion, it's more common to find eutrophic soils with high pH, high content of calcium, magnesium, because of incipient wafting of rocks that are closer to the surface, but also a sandy texture or a higher content of gravels in these soils. And of course, in the areas that receive all this eroded material, they could be thicker, they could register different properties according to which material was eroded. They could be more deeply wafted or can be just incipient wafted according to which kind of material was eroded and then concentrated, accumulated in one specific region. Okay, but also we have some laminar erosion, some runoff that could induce the selective erosion of the fine particles. We call this selective erosion as elutriation. The elutriation, it's one specific process that remove fine particles at the surface. And then sorry guys, and then creates a surface layer with a very high content of sand, gravels, and a very low content of clay and organic carbon and organic matter. And this creates a very unusual surface horizon that it's not, let's say, that's not it not doesn't has high capacity to support life because it has less clay, it can absorb less water, and it has less organic carbon and less nutrients. Okay, I will show some examples of this if these horizons and layers that suffer an intense surface erosion because of the elutriation. We call these areas as desert pavement. It's quite common in dry lands, everywhere. Cold and dry lands, cold and hot, I'm sorry, cold and hot dry lands, both register the desert pavements. These horizons, this surface horizons with a very low content of clay and very high content of sand and gravels, okay? And something that's quite important, that some soils, they register what we call dirty crusts or iron crusts, that are some layers, cemented layers, that cannot be easily wetted, leached, or eroded. In these cases, because of these dirty crusts, you can keep relief stable. You can avoid intense erosion. And a lot of these direct crosses, they are formed in a horizontal way. So they keep the horizontal or way that they are formed in the relief. And in some of these areas, we can register what we call inversion of relief, because some of these areas that form the dirt crust, they are very low areas in the lowlands, and because of the formation of the dirt crust and the action of the erosion, you have what we call the inversion of relief. The areas that was formed in very low altitude now are in the higher position of the landscape, and that those areas that doesn't have the dirt crust, they are intensively eroded, and now they are the lowlands. So the past lowlands now are in the upper area, in the higher area of the landscape, and those areas that in the past are in the highlands now correspond to the lowlands. It's just an inversion. This inversion, it's provided by the presence of the dirt crust. I will show you some examples. It's quite common to see in the tropics. Quite common. And this dirt crust could be composed by basically everything that you can think. Calcium carbonate, of course, iron, but also silicon, salts, aluminum, organic matter. Even organic matter can create dirt crust. It's amazing. So a lot of different chemical compositions, different materials could compose a dirt crust, and the presence of the dirt crust will induce a different kind of relief evolution, okay? This is the graph, it's a plot that shows you a little bit about this interaction between soils and relief. Of course, in areas with a steep slope, with a lot of erosion, sometimes you can find no soil, just bare outcrops, but also some very thin soils. In areas with a high altitude but a flat slope, you induce more wetting, more leaching, and then you can create some thick soils. But in the lowlands, you also can register thicker soils, even thicker than the areas, the flat slopes, because they receive and concentrate materials from all the upper areas. these sediments that are concentrated in these specific zones, they are partially removed by rivers. If the removal is intense, you register thinner soils. If you register less removal, because, for example, the climate condition is quite dry and the rivers, they don't have a lot of competence and capacity to remove materials, you'll create very thick layers of material, of sediments can produce soil. Okay. Um, this is one of the examples of these soils formed in the valleys. I love this kind of soils. I really love to study them because they tell you a lot about the landscape evolution. So you can see in this area, it's the deepest horizons and the deepest layers with some gravels. You can see some gravels here buried, and in this zone you see a lot, like a lot of gravels. It's a layer that's enriched in gravels, and of course you cannot see in this specific picture, but all these gravels, they are very well rounded, and this well-rounded gravels shows you that the transportation, it was in a very far distance to round the gravels. And then, of course, I can analyze the chemical composition of the gravels and find which rock was efferent to create these gravels that now they are buried at this specific depth. And then I can see and understand where a past river run in the past, in which region, in the same region that the modern river runs today, or this past river, he just run in a different region. Okay, this is quite common, especially in dry areas, that the rivers, they change the way through time, the pathway through time. Okay, and it's also quite interesting to see that after this enriched gravel layer, you have another layer without any gravel, just one or two, but basically no gravels. So this change of little content of gravels, very high amount of gravels, and no gravels change are related to the energy of the rivers. So the rivers has more or less energy, and the energy of the rivers depends on the climate conditions, if you have a higher or lower amount of water, but also the distance of this river from the sea level, from the sea level. If you have rivers that has a lot higher altitude and they are quite far from the sea level, yes, you have rivers with more energy, and then they can carry more material with a higher size. If you have rivers closer to the sea level, just 20 or 50 meters above the sea, the energy of the river will be very low. So the rivers, they cannot carry a lot of sediments, or at least they cannot carry a lot of large sediments. So they basically only carry clay or silt, but definitely they cannot carry gravels and sand. So the texture variation of these layers express variations of energy of the river in the past, and the chemical and the mineralogy composition of these layers tells me which material was wetted, eroded, and transported. It's why I think that these soils are amazing, because it tells you a lot about the landscape evolution. I definitely love this kind of soils because they really tells you a lot about the landscape evolution. You can understand a lot about how the landscape evolved through time, and this is quite connected to rivers connections, the river evolution, to the water table level, the sea level, and of course it's quite related to the geomorphology, the geomorphology and the relief evolution. Okay. Yeah, here you can see some examples with more detailed information. And here you can see the gravels, how rounded they are. So we can even describe the intensity of the roundness, how rounded are they. So yes, you can even describe and identify zones with more or less rounded. It's quite common, not in the soil, we cannot see in the soil, but it's quite common to see some ripples of clay in some specific zones, showing that yes, in this specific case, in the past, the river has much less energy than before or than after this specific layer. I also like to date these layers because then I know when this river brings this material and buried this material. Oh, the rippers are the ripples are here. You can see very easily these ripples and the color showing that yes, we have more clay and we have more iron oxides because of this reddish color. Okay, and then we find the last soil formation factor according to Hans Jenny, that is time. And well, we have the first and maybe the most important question for this class today is how much time does soil need to form? And this depends on the process and the soil that we are talking about, okay? For some process, for example, glaciation and podzolization, the reducing of iron or migration of organic matter, just some days will be enough to induce the formation of that soil. Okay, so just some weeks or even less than 1 week can start to form a soil with grayish colors or migration of organic matter. Yes, yes, we can do this very, very easily and fast. So shows you that if you have a lot of water, if you have fluiding conditions, reducing conditions, and organic matter, yes, you can form soils with just some days. Some process, for example, like the melanization, the formation of A horizons with a dark color, provided by a partial decomposition of organic matter. In this case, you need hundreds of years. So it's not a so fast process, but of course, what is 100 years to the planet? Nothing, right? Even for us, it's not a big deal. So yes, we need to consider that we need time to create A horizons. And this is quite important to consider that buried horizons, when we said that, oh, I'm seeing here an A horizon that was buried in the past by some mass movement, let's say in that way. You need to consider that A horizon, it takes some hundred of years to be formed. So the formation of a horizon is not so fast. Means that after the formation of that soil, you need some hundred of years to formation of the A horizon because of the melanization of that section, and then the mass movement brings some material that buried that A horizon. Okay, and some process, they also could take millions of years. For example, the ferralitization. Maybe someone doesn't know what is ferralitization. We'll talk about this in the next classes. Ferralitization is a process that expresses concentration of iron by intense depletion of silica. So an intense depletion of silica destroys a lot of primary minerals, minerals that came from the rocks. So those minerals release iron, and the iron is concentrated as goethite or hematite or any other iron oxide. Okay, so in oxic conditions, I induce, in well-drained conditions, in oxic conditions, I induce a deep weathering and leaching, and basically all minerals are destroyed, and I start to concentrate iron because iron cannot migrate in well-drained in oxic conditions. So I just increase relatively the content of iron because iron cannot migrate. And then we have now a higher content of iron just because iron cannot migrate in well-drained conditions. Okay, and this process is the main process related to formation of oxysols or ferrosols that are quite common in the tropics. So means that those soils that we find in the tropics, they are not young, definitely not, because this enrichment of iron takes time, takes millions of years. So it's quite common to find that these soils, they are really, 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 really old. And means also that if I found a soil with a lot of iron oxides in, for example, very close to Australia, or very close to Antarctica, or very close to Russia, or very close to Andes, means that something it's wrong, or something it's maybe strange, and I need to study a little bit more to understand why that condition formed a soil without a very high content of iron. We have a lot of paleosols in our planet, soils that were formed in past conditions, and they are not related to modern climate conditions that we can see today. Okay. Here we have some examples. So, for example, we can see how clay can migrate from the upper horizons to deeper horizons. And according to some models, you could take some millions of years to register a strong clay migration, okay? To create what we call an argillic horizon, a horizon that express an intense clay migration because the content of clay is quite high in the B horizon. You have some skin surfaces with very shiny faces and everything else. Guys, we need to be careful with this because definitely we don't have a lot of information about how old this process they takes. Okay, we have some very few experiments in lab and very few studies that really can date this process. So we need to consider that we have a lot of variables that could affect the process, and we have a very little information about how long they take. Okay. The same, for example, for the littering or palletization process that are related to an intense accumulation of organic components and then the formation of old horizons. You can see that starts in 100 years, but also can take millions of years to be a thickener of 4 or even higher meters, higher thickness. Yes, you can register some soils that are quite young and have a very high organic carbon content. Some of them has just some 8,000 of years or less than this. And yes, you can find some histosols that register very, very old age because they are formed in paleo conditions, in past conditions. But again, the information that we have, it's quite incipient and not very well established. It's something that I think that we need to focus more in the next years. We need to focus and understand better how long this process takes and which variables could accelerate or reduce the velocity of this process. And just as an addition, today we also have a deep discussion about new soil formation factors, those factors that were not considered by Hans Jenny, but that affect soil formation. So one of the points is that the soil climate conditions, as I said, the soil temperature and soil humidity is not the same of the air or the Earth's climate. And so we need to consider that we should focus much more on soil temperature and soil humidity than the air temperature and air humidity. Okay. Other soil formation factor that's quite important, it's fire. The fire events could induce mineralogical change. They could induce change of physical and chemical soil properties. So they can change the aggregation and they can change the capacity of absorb nutrients. So and they also can produce new minerals that are not formed in the past or before the fire events. So yes, fire is also one of the factors that we need to consider when we talk about soil formation factors. So my suggestion is that when you start to study soils and you are studying the soil formation, please be careful. Please pay attention to the landscape. Please try to consider all possible information that could be interesting to understand soil formation, because the soil formation factors, they are very good when you consider in a general and low descriptive and low detail survey. But when you start to digging deep in the soil formation of one specific area, yes, you need to consider several factors, okay? And maybe some of them were not listed in the past. So a definition that I really like, it's from John Garraud. It's from the US, and I love this definition because it tells a lot. Like, soil is the result of relief and latitude tempering effects of climate, hydrology, non-human organisms, because we also talk about organisms like animals and plants, but we don't say nothing about humans, okay? And parent material over time, unless humans change their characteristics or reset time. I really love this definition because it tells you a lot about everything. Like, we have soils without human action and with human action, and how this human action could be considered. I think that this definition is quite interesting. Okay, but of course it's something that's particular. It's not used by soil taxonomy, it's not used by WRB, but something that you should use for your research, for your life. Like, okay, for me this means much more what soil is than what they said in soil taxonomy and WRB, because here we have a more larger and opened concept and definition. So yes, I need to think in more variables when I'm starting to study soil. Okay. So yes, this is what I have to present you about the soil formation factors. Guys, again, sorry for all time that I need to do something because I'm not feeling good. I'm not feeling very good today. Is there someone with any question or doubts or anything that want to say? No? Is ever? Oh, yes, Anel, please.
After it was
the main problems that we have with boron in the field normally is the
Hi,
way
Prof, can you hear me?
we are offering
Yes.
treatment for the
Yes, I do have a question, but I think it's better that I send you an email.
Of course,
No
yes,
problem. No problem, Sanel. You can email me and I will reply you as soon as possible.
what
Okay.
is the real
All
demand
right.
for
Okay. Okay, guys. So if is everything okay? I will stop the class today for now because, as I said, I'm not feeling 100%. But I hope before the next week I will feel better. Amir? Yes.
It's okay, sir. You are not feeling well today, so it's okay.
Okay. Thank you. Thank you very much. Yeah. I think that I need to rest a little bit. But okay, guys. So see you next week, and I hope in a better shape. So again, I will share the video of this class, the record of this class, and I will also share some references that you should read before the next class. Okay? So,
Yes, sir.
Sir, is it possible to have the slides you shared with us on the video?
yeah, no. I will also share the slides.
Okay.
I'm uploading everything in the Google Drive.
All right. Thank you.
Okay?
Thank you.
Oh, welcome. Welcome.
Get well soon.
Okay, see you soon. See you soon.
Get
So,
well.
guys, have a good week. I hope to see you in the next week. Okay? Bye-bye. See
All
you.
right. Thank you. Ciao.
Thank you. Ciao. Oh, no. Let me just turn off the recording. Stop recording.